This is the first of several videos on torque. Torque, which is symbolized by lowercase Greek tau, is the tendency of a force to cause rotation. Newton's first law for translation. So this is review. An object will continue its translational state, either moving or not, unless acted upon by a net external force. Hopefully that doesn't come as a surprise. Newton's first law for rotation, an object will continue its rotational state, either rotating or not, unless acted upon by a net external torque. So this is going to be another example of some pretty neat connections between translational motion and rotational motion. Newton's second law for translation, there were several versions of it, but there was one. The net force is equal to the mass times the acceleration. Newton's second law for rotation, the net torque is equal to a quantity called the moment of inertia, which is the rotational analog for mass. We'll talk more about that later. And the rotational analog for acceleration is not A, but alpha. So those two are the same equation, one for translational motion, one for rotational motion. The vector equation for torque, and we'll actually use this later on in a video, is R cross F. And we'll define some of these terms here in just a minute. The magnitude of torque, there are several equations you can use to find the magnitude of torque. One of them is RF sine theta. We're here using the cross product, and with the cross product, sine is the trig function that comes into play. You might remember that with the dot product, it's cosine that comes into play. Another one that sometimes you'll see is that tau is equal to R perpendicular times F. Why don't we define a few of those terms and maybe elaborate on what's going on with those equations. So R is a vector that starts at the axis of rotation and extends to the point where the force is applied. One term for R is the lever arm. When using the cross product on R and F, we just saw that on the previous paper, these two vectors must be mentally, anyway, oriented tail to tail. This is different from when we're adding vectors, where vectors must be oriented tip to tail. The variable R perpendicular is often called the effective lever arm. The imaginary line that extends infinitely in the exact direction that the force points is called the line of action of the force. If this imaginary line goes through the axis, there's zero torque. We'll kick all these ideas around as these videos proceed, but when we are multiplying vectors, we need to mentally have the tails of the vectors connected, not tip to tail. All right, quickly let's review. Why is the dot product called the scalar product? And that's because the answer is a scalar. The cross product is sometimes called the vector product, and that's because whenever you do the cross product, the answer is a vector. It has not only magnitude, but also direction. The dot product, which we met when we were dealing with work, the answer has a magnitude, but has no direction. All right, a couple more basics. Are these processes commutative or not? Addition is a commutative process. You learned this in first grade. 2 plus 3, 3 plus 2. Doesn't matter the order at all. What about subtraction? Not commutative. See, 2 minus 5, not the same as 5 minus 2. The order makes a difference. How about division? Not commutative. 3 divided by 7, not the same thing as 7 divided by 3. What about multiplication? Oh, that's commutative, isn't it? 5 times 8, 8 times 5, order makes no difference. What about the dot product? The dot product is commutative. If you have vector A dotted with vector B, it's the same thing as B dotted with A. Order makes no difference. The cross product, and torque is a cross product, not commutative. If you take vector A and cross it with vector B, and we haven't showed you how to do this yet, you do not get the same answer as if you take vector B and cross it into vector A.